Today we're going to take a look at infinite series, and our main goal is going to be to figure out ways of determining when an infinite series converges, that is, ends up equaling a number, and when it diverges, when it doesn't have a number or a finite value. We have so far taken a look at one particular kind of series, that's the geometric series, specifically the infinite geometric series. And we've seen that series we can actually find a value for as long as the absolute value of x, the ratio of successive terms, is less than 1. If that isn't the case, if the absolute value of x is bigger than or equal to 1, the series diverges. So the geometric series is actually pretty special in the fact that we can calculate values for it. We have a formula that tells us what the series equals. And that turns out to very rarely be the case with an infinite series. Often we can approximate the value using a computer, or we can figure out whether it converges or not by using one of the tests that we're going to learn today. The downside is that the tests we're going to learn don't tell us the value the series converges to, just whether or not it has a value. First, we're going to review sequences because when we make a careful definition of what it means for a series to converge, we use sequences to do that. So first, we'll remember that a sequence is a list of numbers. We have our now usual notation for the sequence with the curly brackets, and we're just listing numbers S1, S2, S3, and so on. And now it's important to note that we've got commas between them, right? This is a list, not a sum. One of the things I saw last week were people inserting sums between the terms instead of commas, and that actually turns it into a series instead of a sequence. So we want to be pretty careful about that. Our definition for convergence for a sequence is that if we can make the terms S sub n be as close as we want to some number capital L by taking terms far enough out in the sequence, in other words, taking n large enough, then we say the sequence converges to L. And we have a couple of ways of denoting that. We can just use limit notation. So the limit as n goes to infinity of S sub n is equal to L, or sometimes it's a little quicker, we'll just write Sn arrow L to indicate that the terms are approaching L. Our important and only theorem about sequences is the monotone convergence theorem, and that tells us that when we have a sequence that's bounded, so all the terms are stuck between some minus m and positive m, and the sequence is monotone, so it's either increasing or it's decreasing the entire time, that kind of sequence has to converge. Like the tests we'll see for series in a few moments, it doesn't actually tell us what a sequence converges to. It just guarantees that in certain circumstances, we know a sequence will converge. We take a look at the definition we'll need and the notation we'll need to define series. Informally, a series is just the sum of an infinite list of numbers. So it's like a sequence, except we're adding all the terms together instead of just listing them. Our notation uses a capital Greek sigma to indicate sum. It's kind of a reminder that we're summing things and not just listing them. And then beneath the sigma, we give the starting point of the series. In this case, and in many cases, n will just equal 1. And we continue adding terms out to infinity. So we have infinity as the upper limit there. And what that indicates is that we're going to add term a1 plus a2 plus a3, and we will continue that process indefinitely. Here's an example. We could sum the terms that are the reciprocals of the positive integers. So 1 over n, that would give us 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. We'll pay some special attention to this series in a few minutes. That's a series we call the harmonic series, and it's going to be an important example for us. Here's just another similar kind of example. We could add the reciprocals of the squares and get 1 plus a fourth plus a ninth plus a 16th and so on. One of the things that we'll have to sort out is whether these series actually end up equaling some finite number, or do they continue to grow without bound. One last bit of notation vocabulary is that the a sub n is known as the nth term. Of the series. So the nth term of the first example would just be a sub n equals 1 over n. The nth term of the second example, a sub n, would be 1 over n squared. So whenever you hear a reference to the nth term, that is the thing we're adding up, the terms we're adding up. Now, like most of the things we study in calculus that are unfamiliar, the way we make sense of series is to rely on what we know and take a limit. Now, we know how to take finite sums. If I gave you 10 terms to add up, you could easily do that. If I gave you 100, you could do it. If I gave you 1,000,000, you could do it. May not be pleasant, but it could be done. So we think about starting with a finite sum, and we call those sums the partial sums for the series. So let's take a couple minutes here. The first partial sum is just the first term of the series, so a sub 1. The second partial sum we would get by adding the first two terms together. So there's my second partial sum. The third partial sum we would get by adding the first three terms together. So these are all just finite sums that we can easily accomplish if we know what the formula is for the nth term. We go all the way down so that for any finite sum we could represent that as s sub capital N, where capital N indicates the last term in the partial sum. So if we took s sub 1,000, then we would take the partial sum of the first 1,000 terms. So we call the s sub capital N the nth partial sum, and if we think of them as a sequence, we call it the sequence of partial sums. The idea now behind our definition for convergence is we base it on what the sequence of partial sums does. So if by adding more and more and more terms together, we start to approach some number capital L, in other words, if the sequence of partial sums approaches capital L, then we say the series converges to L, and we can give it a value. We write the series n equals 1 to infinity of a sub n is equal to L. If the sequence of partial sums does not approach a particular value, then we say the series diverges. So one way that we can examine the question of convergence for any particular series is by looking at the sequence of partial sums. We just add more and more and more and more terms together, and we take a look and see if we actually approach some recognizable value. Here's one series we could take a look at, 1 over 2 to the n. That's 1. Since we start at n equals 0, it's 1 plus 1/2 plus a fourth, and so on. We'll also take a look at the series that's the sum of the reciprocals of the squares, and we'll take a look at the harmonic series as well. The way we're going to take a look at this is by using Wolfram alpha, because Wolfram alpha is much better at adding up lots of terms than we are. And then we're going to fill in this table where we start with just two terms in our partial sum, s sub 2, so we'll add the first two terms together. Then we'll take a look at adding the first 10 terms together, the first 1,000 terms, and the first 10,000 terms. We'll take a look and see if we have a pattern, and if we do, we'll call that value that we hopefully recognize capital L. I'm going to go to Wolfram alpha, and it's easy to type in the sum that we need. Here I want the sum, and actually you can type sigma as well, it understands that. And it looks like 1 over 2 to the n, and my first partial sum would be from n equals, sorry, not 1 to 2, 0 to 1. So that's going to add up the first two terms. That gives me 3/2. So I'm going to go back to my PowerPoint and write in the value for S2. About 3/2 or 1.5. All right, back to Wolfram. I'm going to take the first 10 terms, that would be from n equals 0 to 9. I get 1023 over 512, or in decimal form, we see that we get 1.998 or so. So that's already fairly suggestive of what the sum is going to be. Let's do another. For the first 1,000 terms, I would go from n equals 0 to 999. We get a really big fraction if we want to take a look at that. And then notice that our decimal approximation is pretty clear, right? We're going 1 point and then more nines than Wolfram Alpha cares to show. So let me just indicate that on the table. So this would be 1.999 and so on. We'll get the same thing for the first 10,000 terms. We'll get 1.99 and then more nines than we can look at. So we should go ahead and declare the value of this sum equal to 2. The sum appears to be converging to 2. It's also worth pointing out that this is a geometric series, and it's one of the few that we can check our work with. So we would have the value is a over 1 minus x. The a is 1. The x is 1/2. And in fact, 1 minus 1/2 is 1/2. Flip that over, and we get 2 for the value of the series that way as well. So it's nice to see that our definition for convergence, examining partial sums, in other words, adding more and more and more terms, agrees with what we have for the formula for the geometric series. Now the pattern for the 1 over n squared sum is not going to be quite so clear. Let's take a look. Well, we don't need Wolfram for S sub 2, I think. We could have 1 over 1 squared plus 1 over 2 squared, that's 5/4, or about 1.25. The first 10 terms I will let Wolfram help with. So we get to Wolfram, we have to change the form of the sum now. Instead of 2 to the n, I have n squared. So I'm taking the sum, 1 over n squared, n equals 1 to 10 in this case. All right, the result I get is about 1.549. I guess I can round that to about 1.55. So 1.55 or so. And now I want to see what happens if I add more terms. So S sub 1,000 is the next one in our table. So I'll go from n equals 1 to 1,000. And if I add up all the squares all the way out to 1 over 1,000 squared, well, Wolfram will give you the fraction. But what's more important here is the decimal approximation. It's 1.6439. So let me add that to the table. 1.6439. And let's do one more. What happens if we add all of the terms, 1 over 1, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, all the way out to 1 over 10,000 squared? decimal version 1.64483. So this is one where we probably don't recognize the number, but we can tell we're getting close to something that's about 1.64. So we could either say the series converges to something about 1.644, or if you happen to recognize this one, it's the same as pi squared over 6. I'll let you check that on your calculator. All right, our last example is to take a look at the sum of the reciprocals of the positive integers, in other words, the harmonic series. Well, let's see what this one does. All right, so I'm just summing 1 over n equals 1 to 2. That one's not so hard, that we get 1.5. I could go n equals 1 to 10. I would get about 2.93. If I go out to 1,000, as a decimal, I get about 7.49. If I go out n equals 1 to 10,000, I get about 9.78. This does not seem to be settling down to any particular number. Let me go out to, say, 1,000,000. So if I add the first 1,000,000 reciprocals together, I get about 14.39. Well, Wolfram is graphing the partial sums just below the decimal approximation, and it's showing that the partial sums seem to be continuing to increase without bound. We could go out to, say, 1,000,000,000,000. At some point, Wolfram will not enjoy this, but it looks like 1,000,000,000,000 is okay. If we go out to 1,000,000,000,000 terms, then we have grown to about 28.2. So this is our first example of a series that diverges. The partial sums are not approaching any particular number. This one continues to grow without bound, even though it's growing really, really slowly. So if you can imagine trying to actually add up 1,000,000,000 terms with your calculator, it wouldn't get you very far. It'd get you to about 28.2. Let's try a quintillion. It may not do this, but it does. So after a quintillion terms, we would have grown to about 42. So still not very big. So you can kind of imagine that this is really kind of creeping towards infinity. It's even hard to comprehend how slowly this is really growing. But this is saying that, and we'll prove this actually in a minute, that we could add enough terms to make the sum be bigger than 7 trillion. We can make the sum be bigger than 400 quadrillion. We can make the sum be bigger than any finite number if we take enough terms. And these examples are giving you some idea of how many terms that would require. All right, so I didn't fill in the table for this one, but here we can say L equals infinity, or we could write diverges. All right, before we start getting into tests for convergence for all of our different series, we'll go ahead and review the one example we'll have, at least for a while, of a series whose value we can determine. And in terms of series, it's the sum n equals 0 to infinity of a x to the n. And we know how to find the value. It's a over 1 minus x, as long as the absolute value of that ratio is less than 1. And we confirmed that this matches up with our definition for the convergence of series. in terms of partial sums. A couple of facts about series that we'll use most of the time without comment. These are theorems that we can prove based on the definition of convergence. But the idea is if you have two convergent series, the series of the A terms converges to L and the B terms converge to M, then when you take the series of their sum, that's the same as the sum of the series. So if you took the series n equals 1 to infinity of an plus bn, you would get L plus m. So you can separate convergent series this way. Secondly, if you have a convergent series and you multiply all the terms by some constant, then you can factor that constant out in front of the series, just like you could for a finite sum, and the value would end up being that constant times the original value. And finally, whether or not a series converges is unaffected by changing, adding, removing any finite number of terms. So as an example, if we know a series A sub n converges, then if we discarded the first 99 terms, the series would still converge. This can be a little tricky to think about because we're not saying they converge to the same thing. They actually typically won't, right? If you leave off 100 or 99 terms, you'll change the value of the series, but it'll still be finite, regardless of how many terms you change, add, or delete, as long as it's a finite number of terms. All right, so we're going to go take a look at our first test. This is called the nth term test for divergence. And the idea is that if you take a look at the nth term of a series, not the sum, but just the nth term by itself, and as n goes to infinity, if that limit is not 0, the series can't converge, it has to diverge. So the slide animation here is a little bit out of order, but here's our first example. The series sum of 1 minus 1 over n. If we take a look at the limit as n goes to infinity of a sub n, in this case the nth term is 1 minus 1 over n, we know that this piece, 1 over n, has to go to 0. So the limit of the nth term is 1. Well, 1 is not equal to 0, and so by the nth term test, the original series has to diverge. Here's a second example. If I take a look at the limit as n goes to infinity, minus 1 to the n, well, that bounces back and forth between minus 1 and plus 1. So it has no limit. Whenever something bounces around indefinitely, that's a does not exist for the limit, and certainly does not exist is not 0. So this series diverges as well. As a final example for the nth term test, we take a limit as n goes to infinity, 1 over n, that is equal to 0. This is something that's really important to remember. If you do the nth term test, it's never a test for convergence. So the nth term test says if the limit of the nth term isn't 0, the series diverges. If the limit of the nth term is 0, the test does not apply. You could have a divergent series, you could have a convergent series, but the nth term test is not going to help you figure it out. Now, it's almost impossible to make it through Calc 2 without messing this up at least once and looking at the nth term, saying the limit goes to 0 so the series converges. But I just want to emphasize that that is not a proper use of the nth term, and if you get something that equals 0, you have to move on to another test. Since we have an example here where the limit of the nth term is 0, we're going to focus now on this harmonic series and show, by thinking about the partial sums, that the series really does diverge. So I've written out the first several terms of the series, and the idea behind what we're about to do is to show that if we go out far enough in our series, we can make the partial sums be as large as we want. We start by just taking a look at the first term, and we'll note something that's not terribly impressive, and that is the first term is bigger than a half. We'll do the same for the second term. That's also bigger than or equal to a half. And now we do something a little different. The next two terms, if I add them together, since 1/3 is bigger than a fourth, the sum of them is bigger than a fourth plus a fourth. So that group of two terms is also bigger than or equal to a half. Next, we look at the next four terms added together. 1/5, 1/6, and 1/7 are all bigger than an eighth. So if I add all four together, I get something that's bigger than 4/8. So those next four terms are also bigger than or equal to a half. And then as a final extension of this pattern, 1/9, 1/10, 1/11, and so on, they're all bigger than a 16th. And so if I add those 8 terms together, I know I have something that's bigger than or equal to 8/16, which is the same as a half. And so I've got something that's bigger than or equal to a half there as well. If I took the next 32 terms, I would also have something bigger than a half. And so what I'm showing is that if I go out far enough in the series, I'm getting something that's bigger than a half, plus a half, plus a half, plus a half, plus a half, and that we know will grow without bound. So the series itself is bigger than the sum 1/2 plus 1/2 plus 1/2 and so on, and that sum is infinite. So if we have a series that's bigger than something we know is infinite, it's also infinite. This is just a reminder now that the nth term test did not apply. So if we had incorrectly said the limit of 1/n equals 0 so the series converges, well, we're seeing here that this shows that's not always the case. The harmonic series is a series whose nth term goes to 0, but is nevertheless divergent. Our next test is called the comparison test. This one relies on having a series that you already know converges or diverges, and then comparing some unfamiliar series to it. So the full version here is that if we have an inequality 0 less than or equal to a sub n less than or equal to b sub n for all n, then if the series of the larger terms converges, so does the series of the smaller terms. This works the other way in that if the series of smaller terms diverges, then the series of larger terms also has to diverge. Right? If the smaller one goes to infinity, so does the bigger one. Let's take a look at a couple of examples. So here's an unfamiliar series. The nth term is n plus 2 over n squared. And we're going to note that n plus 2 is bigger than n, so n plus 2 over n squared is bigger than n over n squared. That's equal to 1 over n, which we know is always bigger than 0. So here we have our a sub n, and we're comparing our b sub n to it. So the series made up, the original series made up of terms n plus 2 over n squared is a larger series than the series made up of the terms 1 over n. We're comparing our given series, our unfamiliar series, with the harmonic series. We know from our previous work that the harmonic series diverges. That means our original series diverges by comparison. Sometimes I'll leave the limits off of my sum just to make it quicker. Right, so a complete answer to any question of convergence for a series involves a conclusion. What does the series do? Here we have shown that it diverges, and not just a conclusion, but a reason for it. So here our series n plus 2 over n squared diverges by the comparison test with the harmonic series, which we already know diverges. There's a second one that's going to be a little different. So this is an unfamiliar series. Let's see how we could apply the comparison test here. I know that all of these terms are bigger than or equal to 0. There are no negative numbers anywhere. And what I'm going to do is take a look at the denominator. I'm going to remove that square root of n. That means I've made my denominator smaller, so I've made the entire fraction larger. And now this nth term we're comparing to, I can rewrite as 2/3 to the n. So since the series made up of terms 2/3 to the n converges by the geometric series, so does the original by comparison. So I have a conclusion, and I have a reason for it, the comparison test, and I've shown my use of the test because I have to check to see that I'm applying the test correctly. Our next test takes advantage of our knowledge of how to do improper integrals. The idea of this test is that if we can visualize the terms in our series as the values of a decreasing non-negative function, then we can figure out the convergence of the series by examining the convergence of the improper integral. This one's a little harder to state and kind of figure out the notation than it is to apply. So let's get right to an example. All right, so the series 1 over n squared, we've established at least a belief that this series converges by examining the partial sums. This is the one that converged to what I claimed was pi squared over 6. Let's use the integral test to show it. So if I think about the function f of x equals 1 over x squared, that is a function that is non-negative. And as x gets bigger, 1 over x squared gets smaller, so the function is decreasing. So I'm checking off the requirements of the theorem. And if I plug in into the function, I get 1 over n squared. That's my a sub n. So the integral test says the series and the integral both converge or both diverge. So I take a look at the limit as b goes to infinity, integral 1 to b, 1 over x squared dx, antiderivative for 1 over x squared is minus 1 over x. If I evaluate that limit, I end up getting 1, because minus 1 over b goes to 0 as b goes to infinity. So I have a convergent improper integral. And so does the series by the integral test. We can use the integral test to verify that the harmonic series diverges. Let's do that. Here the function will be 1 over x bigger than 0. Decreasing, that's true, because as x gets bigger, 1 over x gets smaller. And does it generate the nth term? If I plug n into the function, I get 1 over n, so that's okay too. So I need to do an improper integral. Limit b goes to infinity, integral 1 to b, 1 over x dx. Integral of 1 over x is the natural log. We've done this one before. Since the natural log of 1 is 0, this boils down to finding, you define the limit as b goes to infinity, natural log b, the natural log function goes to infinity. So we have a divergent improper integral. So the series made up of the terms 1 over n also diverges. And it diverges by the integral test. Now if we apply the integral test to a certain type of series, then we get what we call the p-series test. This one is really easy to apply if you recognize that you can apply it. And this is kind of a restatement of something we've actually done in one of our previous worksheets. We took a look at integrals of the form 1 over x to the p and saw that those integrals converged when p was bigger than 1 and diverged when p is less than or equal to 1. So the integral test gives this result as a corollary, that the series 1 over n to the p converges if p is bigger than 1, but diverges if p is less than or equal to 1. A couple of examples. We can rewrite the series of the reciprocals of the square roots as 1 over n to the 1/2. That makes this more clearly a p-series where p is a half. That's less than or equal to 1, so we have a divergent series. We could also have done this one by using the integral test with 1 over x to the 1/2. That would be a little bit of a waste of time. Or we could have done it fairly quickly with a comparison to 1 over n. Since 1 over square root of n is bigger than or equal to 1 over n, and the series 1 over n diverges, by comparison this series would also diverge. So with a lot of these, we'll see that there are multiple tests that we could use and still get a correct conclusion. One more example of applying the p-series test. Here we have to recognize that n to the minus 1.01 is the same as 1 over n to the 1.01. That reveals p, in this case, to be 1.01. That's bigger than 1, so this series converges. Almost there. We've got a couple more tests to take a look at. One is the alternating series test. This one says if you're adding up terms that alternate between plus and minus, and those terms go to 0, then you'll have a convergent series. So let's take a look here at the series that is the harmonic series, but the terms are alternating. So it's a little bit different. Here, my b sub n is 1 over n, because the minus 1 to the n is what's causing the signs to change between plus and minus. So these are terms that are bigger than 0, that go to 0, and are decreasing. So the 3 hypotheses of the test are satisfied. We have alternating terms that are made to alternate by the minus 1 to the n piece. And if we examine the terms without that minus 1 to the n piece, then 1 over n is bigger than 0, goes to 0, is decreasing. So the series of alternating terms converges by the alternating series test. We have what we call the absolute convergence test. This is a test that says if you turn all of your terms into positive terms and that series converges, then so does the original. In other words, if the sum of the absolute values of your series converges, so does the original series. Here's an example. It's not an alternating series because we have one positive term followed by 2 negative terms, and then a positive and 2 negatives, and so on. So it's not an alternating series, but if I take a look at the sum of the absolute values of all of the terms, that gives me a sum we've seen before, the sum 1 over n squared from n equals 1 to infinity. This one we already know converges. We could say it converges by the p-series test or by the integral test. And so the original series converges by the absolute convergence test. All right, our last test, and this I hope will become one of your favorites because the good news about this one is that it's fairly straightforward in the way you apply it. That's not to say it's easy, but with the comparison test, for example, you have to have kind of in your head a series you know is pretty close to the one you're looking at, and you know what it does. This one just requires that you do some algebra correctly. The idea here is if we look at the limit of the ratio of successive terms, that's what this is, the limit of the ratio of successive terms, the n plus first term divided by the nth term. And if we take that limit and get something that equals capital L, that capital L can tell us whether or not the original series converges. If we get something less than 1, it will converge. Bigger than 1, it won't converge. Equals 1, unfortunately in that case the test fails and we need to try something else. Here's an example of how to use the ratio test. One of the reasons I put the factorial sequence on the worksheet a couple of times ago is that it's going to come up a lot when we're dealing with the ratio test, and also when we start looking at what are called Taylor series. For now though, we just need to take the limit as n goes to infinity, the n plus first term divided by the nth term. That's all in absolute values. Now, this is a series where all the terms are positive, so I can just drop those absolute values. But it's good to get in the habit of having them there. They will be important. So this is the same as 2 to the n plus 1. Now, n plus 1 factorial is the same as n plus 1 times n minus 1, and so on. So it's the same as n plus 1 times n factorial. Since I'm dividing by a fraction, I can bring that up by multiplying by the reciprocal. And here we get a lot of nice cancellation. The n factorials cancel, and 2 to the n plus 1 cancels with the 2 to the n, leaving me with just a 2 to the first, or 2, in the numerator. So after the canceling, which will often happen with the ratio test, I'm looking at finding the limit 2 over n plus 1, and that limit must be 0. As n grows to infinity, 2 over n plus 1 goes to 0. So we have L equals 0, and because 0 is less than 1, the series converges by the ratio test. All right, that's the end of a long presentation. We have several different tests for series. We have to understand the definition of what it means for a series to converge. We have to remember how to apply all of these tests. And the hardest part maybe is developing some intuition about what test to use. We'll start working on those things in class on Wednesday when we start working problems. But it's going to require a little bit of patience. So I hope you come to class on Wednesday ready to tackle some problems, and perhaps being a little patient with yourselves if you find this material a little bit frustrating. That's generally a sign of good mental health because it is hard material. It's going to take a little while. We'll start that process Wednesday, continue it on Friday, and I will see you then.